Hey, I'm Chris, and this is a quick start to Rust. It's meant to give you an idea of what Rust is like, as well as communicate some high-level ideas behind what makes Rust interesting. Each section will not be comprehensive, that's for later, but you should get a feel for what it's like to write and maintain Rust. If you're interested in using Rust after this, there's more in-depth content on the way over on rustadventure.dev. And with that, let's start off by having a brief discussion about installing Rust and what tools come with that. But first, if you don't want to install Rust just yet, you can head over to play.rustlang.org, which is the Rust playground. This will let you write and run Rust in the browser with a few restrictions, such as limited selection of third-party crates and limited resources. For everyone else, to install Rust on your local system, head over to rustup.rs and follow the instructions for your platform. Rustup is how you manage installed Rust versions and their associated toolchain. This includes tools like Cargo, Rust's package manager, as well as tools needed for compiling different targets, like wasm, and formatting, linting, or documenting your Rust code. Running Rustup will show you a list of subcommands if you've installed it correctly, and it is on your path. Once you have a version of Rust and its toolchain installed, building a Rust program is a matter of running cargo build. This will, by default, build for your local system, so if you're on macOS, it will build for the macOS target. If we wanted to target another platform like wasm in the browser instead of our native system, we can add the desired target using Rustup. Here we'll use the wasm32 unknown target, since that's a common target to run in the browser, and will produce a wasm file for us. Once installed, we could use Cargo to build a Rust library into a wasm file that runs in the browser using Cargo build with the target triple. Now, Cargo is Rust's package manager, but that's underselling it a bit. Cargo is capable of calling out to a suite of the Rust toolchain tools that we installed with Rustup, as well as community-maintained subcommands. Some of the useful subcommands that call out to components that were installed with Rustup include Cargo build, Cargo clippy, Cargo format, and Cargo doc. This is just a subset of the tools and includes building your programs, linting, formatting, and documentation building. There are a wide array of community Cargo subcommands as well. These can be installed with Cargo install directly from the package registry crates.io. One example is Cargo generate, which I love. This is a more sophisticated package scaffolding tool than the built-in Cargo new subcommand. The Cargo generate subcommand can be installed with Cargo install, and then we can use it to grab a demo template from the Rust Adventure GitHub organization and scaffold the new project locally. This project doesn't do anything particularly interesting, it's just here to show off Cargo generate and Cargo subcommands. Rustup also installs Rust Analyzer. Rust Analyzer is the language server protocol implementation for Rust. That is to say, Rust Analyzer is what provides your IDE or editor of choice with type checking, diagnostics, code assists, go to definition, refactoring, code completions, and more. Rust Analyzer can also power inlay hints, which expose the types of the data in variables across your program, as well as triggering auto-formatting on save. One neat trick Rust Analyzer has up its sleeve is converting a string of JSON into a reasonable Rust data type representation. This string can be pasted into an editor powered by Rust Analyzer and turned into the following struct definition, which isn't perfect, but is a great starting place. To kickstart a new Rust project, we'll use Cargo new with either the bin or lib flags. These indicate whether the project will be a binary that can be executed or a library that will be included in another project. The name of our package will be quickstart, which will create a quickstart directory to hold our project. Cargo new creates two files, cargo.toml and source main.rs. You can see the file layout here with cargo.toml at the root of the directory and main.rs in the source directory. The cargo.toml is the package manifest, which contains details like the name and version of the package, the edition of Rust used, as well as any dependencies. Editions are major releases of Rust, and Rust puts one out about every 3 years, so the latest edition is Rust 2024. Rust is actually on a rolling release train release cycle, so every 6 weeks we get a new Rust version, but anything that would be a breaking change is saved for one of the larger editions. As for main.rs, it's the default entry point for a binary crate. A Rust package can contain multiple binary entry points, and often these extra binaries are stored in a different location, like source bin. Files in this location use the file name as the binary name by default. This file must have a main function, which will execute when our binary does. In this case, we use a macro called printline to print hello world out to the console. We know printline is a macro because of the exclamation point at the end, and we can run this program with cargo run. Some notable information in the output here is that we built with the dev profile, which is unoptimized and includes debug info. By default, Rust programs compile with the dev profile. To enable a release build with optimizations, which will run faster, use the release flag. The output now notes that we built with the release profile and it is optimized. The cargo run subcommand combines cargo check with cargo build and then runs the built binary, which means that when we cargo run, we also get the built binary in our target directory. The binary for our quickstart program gets built at either target debug quickstart or target release quickstart, depending on which profile it was built with. And once built, the binary can be executed directly. Often the difference in execution speed between the dev profile and the release profile is significant. Consider this program which repeatedly sets the value of result in a loop. It's not technically interesting, but it proves the point. Running this program in dev with cargo run takes significantly longer than running in release with cargo run release. That brings us into Rust the language. And Rust is a primarily expression-based language. This shows up in examples like this one, where the if expression returns either 1 or 5 depending on whether its test is true or false. Expressions can produce a value and will return the last value produced in their scope. For example, we could write a block expression that defines a variable, then uses it to do some math, and then returns the value. This pattern can be used to encapsulate complex data initialization without leaking intermediate variables into the rest of the code. Moving on from expressions, in Rust, data has a single owner. This means a single variable is responsible for the lifecycle of a specific piece of data. In this piece of code, the numbers variable owns the vec data. A vec in this case is a list of data that can be added to or removed from. When using the vec data in our application, we can either share references to it, which retains ownership of the data in numbers, or we can move it to a new owner. The prints numbers function takes ownership of the data, so in this case, we move the data. This means that calling prints numbers twice would fail to compile, because the first prints numbers moves the data out of the numbers variable into the vec of numbers variable in the function. This means it's no longer in numbers for the second prints numbers call to access. This code will result in a compile error. The compiler warns us about the program having moved the data, while also providing suggestions for how to fix that. In this way, Rust will, at compile time, guarantee your data isn't changing out from under you while operating on it, because the compiler knows which functions are taking ownership, which are mutating it, and which have read-only access. Ownership turns this problem into something the compiler can check for you instead of something you need to keep track of in your head while programming or doing large refactors. This kind of thing yields huge benefits for teams which can merge PRs, knowing that one person's merge won't silently invalidate another person's data usage in their PR. The compiler will keep track of these issues for you. So when it comes to our example that currently has a compile error, we can fix it in one of 3 ways. We can clone the data, creating a second duplicate value with a different owner. We can move the data back out of the function by returning it, or we can share a reference, which allows a function to temporarily access the data in a read-only or mutable compiler-checked access pattern. Let's cover cloning first. Cloning the data allows us to pass a duplicate value into the first function while moving the value in numbers into the second function. This is a good option if the values are lightweight or if multiple copies are needed. We can also continue moving the data once we've moved it into the function by moving it back out. The prints numbers function can take ownership of the vec of I32s and return it as the return value. The debug macro in this case also takes ownership of the vec of I32s and returns the value it took ownership of. So remembering that Rust is primarily expression-based, the value returned by the debug macro is in turn returned from the function. Since we're moving out of numbers, we have to create a new variable to own the returned value of prints numbers. This new numbers variable is what we'll pass into the second function, moving the data again. And finally, for option 3, we can use references. Passing a reference provides temporary read-only or read-write access to the value in numbers, while numbers retains ownership of that value. There are 2 kinds of references in Rust. Shared references, indicated by just an ampersand before the variable name, and exclusive references, indicated by an ampersand with MUT or mutable. Shared references allow many users to access the data at the same time, while exclusive references only allow a single user at a time. We can rewrite our function to accept shared references as arguments since we don't need to mutate the vec, and pass in shared references to the data in numbers. This lets us avoid cloning and creates clear expectations for the prints numbers function. Since the prints numbers function only accepts a shared reference, it cannot mutate the vec of I32s. But idiomatically, if we're going to accept a vec of I32s as an argument, we'll likely want to accept a slice instead. This is because many container types can easily be turned into a slice of their items. Accepting a slice as an argument places fewer restrictions on how the data passed into the function is stored. Consider the following example, which has one key difference from the shared references example above. The argument to prints numbers is a slice of I32s. A slice then is a view into another container. It's a view into somebody else's data. In this case, we're passing a slice of all of the vec items into the prints numbers function, and this produces the same output we've been seeing. Both calls to the prints numbers function print all of the vec items. This is possible because a vec implements deref for slice. We'll talk more about traits like deref later in more depth. The important information here for now is that there's an explicit opt-in to be able to deref a shared reference to a vec to a slice. As an ergonomic improvement, deref coercion enables Rust to use the deref implementations that we define to coerce a shared reference to a vec into that slice. This happens in our example because the function that we wrote accepts a slice and the argument we passed in was a shared reference to a vec. But we could also use a subslice, which slices a subsection of the items in vec. Slices can be taken with range syntax starting at index 0. In this case, we use two ranges, one for the function call, an exclusive range, from 0 to 1, which results in viewing a slice of one item, the item at index 0, because the end of this range, index 1, is excluded. We could also use an inclusive range using 1 ... equals 2 syntax. This views the items at indices 1 and 2 because 2 is now included in that range. This results in the slice containing the first item being printed out by the first function call and the second function call printing out the second two items. These are completely separate slices that could include any of the items. Now, there are many types that implement deref and thus have owned and shared variants that can take advantage of deref coercion. A string, for example, owns its data similar to a vec. Thus, similar to the way we can take a slice of the vec, we can take a string slice of the string. Note, however, that because Rust's strings are UTF-8, they don't implement indexing, only slice indexing. This means that taking slices of strings likely isn't what you want to do, unless you know that you have ASCII-only content, as otherwise you can end up in the middle of UTF-8 code point boundaries. There are some really nice crates though, like Unicode segmentation, which handle UTF-8 appropriately. Another type that has a similar configuration is pathBuff and path, where pathBuff is the owned data type and path is like the slices. Here we create an owned pathBuff from a string literal, which could fail, so we unwrap. We'll talk more about error handling later in a dedicated section. This pathBuff implements deref for path, so we can again take advantage of deref coercion. However, this time pathBuff doesn't implement index or slice index, so we can't take subslices. And so far we've talked about Rust's default behavior, which is move semantics. I've used the word move a couple times already. This is what happens when we move our vec through the prints_numbers function from earlier. Ownership passes from the initial variable into the function and so on. But sometimes this isn't what you want. For example, integers are often only used for the value of the integer. If you want to add two 5s together, it doesn't matter that you got a copy of a 5 from another variable. We're going to spend a little bit of time talking about data structures in Rust, which includes primitives and your own custom data types. If you've written another programming language before, this could be repetitive for you. Rust has scalar primitives as well as a rich type system of custom data types that can be defined using structs and enums. For example, numbers in Rust have specific sizes. An I32, for example, is a signed integer with 32 bits available to define the number. Since numbers have associated sizes, the min and the max values they can represent are smaller or larger based on that size. An I32 has specific minimum and maximum values similar to the way that a U8, or an unsigned 8-bit integer, has a minimum value of 0 and a maximum value of 255. Also interesting is the idea of numbers that use specific values to store additional data. For example, if we knew we would never have a 0, we could specify a variable as the type non-zero U8, which has interesting implications in that option non-zero U8 and U8 have the same size in memory. This is because the none value for the option can be stored as the 0 value, which is super cool if maybe a little bit advanced. Characters also have their own type in Rust. A char is a Unicode scalar type in Rust. Character literals are defined using single quotes. Here, given a string, we can get an iterator over the characters using chars. In this case, we're checking to see if a character is one of two values using character literal syntax. Note that because char is its own type, we can't compare against a string literal, like s, and must use a character literal, which is single quotes. Rust's true and false values are written as true and false, lowercase, and the type is called bool. Super surprising, I know. Which brings us to something a little bit more interesting, arrays and tuples. Arrays in Rust are fixed size collections of items of the same type, while tuples are fixed size collections of potentially different types. If you want an array that you can push items into or remove items from, you probably want a vec instead. Here are two ways of initializing an array of length 3. The first copies the value 0 to fill all the slots. The second uses 3 separate defined values, and thus doesn't need to specify how long it is. Getting a single value from an array can be done by indexing. For arrays, this uses square brackets. But while arrays can only hold one type of item, tuples can hold many different types of items at the same time. Here we have an F32, a string slice, and a car in a tuple. Running this program will dump the tuple out and show that indexing into a tuple happens without the square brackets, which gives us a nice segue into structs. Creating your own data types can be done using struct and enum keywords. This is how all the data types we've used so far are built except for the primitives. A vec, for example, is a struct. A string is also a struct that contains a vec. Result and option are enums, and so on and so forth. A struct is a collection of fields that can be defined with named fields, unnamed fields, or no fields. The latter two options are often referred to as tuple structs and unit structs. Here are a few ways to construct struct types and values, along with a debug implementation, which we'll talk more about later. Similar to tuples, tuple structs can be accessed by index. Structs with names can be accessed by field name, and unit structs are zero-sized types with no fields. But we can still debug them. An enum, on the other hand, is a contrast against the struct because an enum is a choice between multiple variants. For example, we can define a set of colors and then use a specific variant. This is great when you have to pick one of many options. Now, this color example shows off a set of unit variants, which is fairly common usage, especially in other languages. But enums in Rust can contain all sorts of data, just like structs. Here we have an enum where the variants are a tuple struct, a unit struct, and a struct with fields for parrot. Given a parrot, the program now outputs, my parrot's name is Jose. I don't actually own a parrot named Jose, but I do stream developing this content on this channel if you want to come hang out with us. And one of our viewers' parrot's names is Jose. This brings us to the combination of structs and enums. Structs can contain fields that hold enums, and enums can define variants that hold structs. Using structs and enums together can satisfy a wide array of data structure requirements. But how do we define functions that work with these data types? This is where impl blocks come in. Types like structs or enums can have functions associated with them using these impl blocks. Although it's not required, you can just have free-floating functions that take in these structs. For example, we can define a function that takes a shared reference to have an animal say its name, or takes an exclusive reference to mutate the values, dyeing the color of the animal, or finally takes ownership and doesn't return the value, thus causing it to drop and be inaccessible afterwards. These functions use the self keyword in a couple of different ways, including a shared reference to self, an exclusive reference to self, and the owned value self. These all refer to the type the function is being implemented for. So since we're implementing for animal, if we use self, it means animal. And there's one big key that I would give you when working with structs and enums and creating your own data types, especially just starting out. And that's when working with structs, you can choose to define structs using owned data like strings or references like string slices. So when you're just starting out, prefer owned data almost always. This makes it easier to judge which variable actually owns the relevant data. Of course, using references in structs can be useful, especially for zero allocation parsing and other use cases. References in struct definitions also require more understanding of which variable owns the data and how long the references are going to live for. Moving on to error handling. In Rust, there are two major classes of error, recoverable errors and unrecoverable errors. If the error is recoverable, a function will return a type that you can continue to operate on. If the error is unrecoverable, the program will panic and exit. A program can panic explicitly if something goes wrong using a variety of macros. Some examples include panic, to do, unimplemented, unreachable, and an assert equals macro that fails. Some of these are useful for production code, such as assert equals, which can assert an invariant about what you expect to be true. But when writing code that isn't finished, it can be very useful to use the to do macro. This is effectively a shorthand for writing panic with a customized error message. When this code is run, if the avian parrot match arm is hit, it will panic with the message not yet implemented, memory for parrots. The other useful part of the to-do macro is that it will short-circuit the type checking, allowing this program to compile at all. If the to-do macro didn't exist in this example, the parrot match arm would return unit, which is incompatible with the string slices returned from the other arms. We'll cover control flow more later, but in the meantime, understand that a match expression like this must return the same type from all arms. The two major types for dealing with recoverable errors are option and result. These are both enums that contain a success value in one variant and an error value in the other. An option returns a value that may or may not exist. Rust doesn't have a concept of null or undefined or other similar values, so option is how a potentially missing value is represented. A result, on the other hand, can hold any two distinct values in its variance. Result OK represents the successful value, while result error represents the error value. Often, and pretty idiomatically, the error value in a result is an enum representing multiple things that could have gone wrong. But it is not required to be any specific value, and could be a usize, for example. In this demonstration, if you do index access on a vec and you use an index that doesn't exist, the program will panic. There's an alternative function called get that will instead return an option. This means the resulting value will be option some if successful and option none if not successful. The program here prints out two values using get before panicking on the direct index access, which is out of bounds. Similarly, a result is returned by vec get disjoint mute. The get disjoint mute function returns exclusive references to multiple separate items in the vec if it can, otherwise it returns a get disjoint mute error. This function can give us non-overlapping exclusive references to different items. But if we ask for the same item multiple times, we can't get multiple exclusive references to the same item. So we would receive a result error variant with a get disjoint mute error overlapping indices variant inside of it. It turns out that options and results are so similar, it's common to convert between the two by dropping or adding an error message. Given an option, an error message can be added, converting it into a result, using option OK or. Whereas given a result, the error message can be dropped using result OK. And dealing with option and result is so common that there's syntax for return if the value has an error. This is called the try operator and can be used with both options and results. When writing a function, the return type can be an option or a result. If the types that we're using match, such as in the case of numbers.get4, then we can use the question mark or try operator to unwrap the value if it's some and return none otherwise. This function works on slices of length 5 or more and returns none in other cases. There are multiple levels to error handling too. It's possible to be as granular as is useful when handling errors in Rust programs. For example, an application level error in a CLI tool might only care about reporting errors to users. For application level error reporting, we can take advantage of one of many error reporting crates on crates.io. In this case, we'll use anyhow. Anyhow provides a new error type and a type alias, anyhow result, that uses the anyhow error as the default error type. Anyhow also implements from for any error. When we say any error in this case, we mean any type that implements the standard library error trait. In turn, this means that any type that implements error can be returned using the try operator if the function returns an anyhow result. Consider the following example. The program uses anyhow result as the return type, enabling the handling of many different kinds of error types. The first action here that can fail is an attempt to read a numbers.txt file. If the file doesn't exist or doesn't have the right permissions, a result error variant containing an IO error is returned. In this case, we take advantage of anyhow's ability to add additional context to errors when they happen, before using the try operator to unwrap or return the error. If the file doesn't exist, the application prints the error out along with the context we added. In this case, it's assumed that numbers.txt is a file like the following, containing I32 values on each line. But also in this case, we have a rogue float value, which will fail to parse. Since we're iterating over each line with a for loop and attempting to parse it into an I32, we can again add context to the potential parse int error that will happen when we encounter the float. Doing application level error handling this way means there's very little additional setup, and we can also still add context to the errors as they happen. By contrast, it's often the case in libraries that you want to be more specific about the errors that can be returned or occur. For this, we can build our own error types at any granularity. An error type for the entire library crate is a fairly common approach, but you could do an error type for every function if you were okay with the extra overhead of writing a bunch of different error types. Similar to how we saw get disjoint mute error was an enum with multiple variants, we can construct our own error types. Typically, this is made easier by the crate ecosystem, which can derive implementations of the standard library error trait for you. Specifically, this error is an extremely common crate to use, since it makes writing error variants easier. There's also additional options like snap-foo, but we won't cover those today. Given a hypothetical data store library crate, a custom error type could look like this. This error is providing a derive macro and a set of attributes to make defining these errors easier. In this case, we see a variety of error message format strings that can optionally include data from the error variant itself. It is also the case that we'll have to interface with other errors, such as those from reading a file. This error provides a from attribute macro that, when used, results in a from implementation that connects the relevant error to our custom error type. In this case, that means we can use the try operator on an IO error, returned from operations like read to string, if our function returns our custom error type. In that case, we wrap the whole IO error in a new variant of our custom error automatically. Moving on to iterators. When looping over a collection's items like a vec of I32s, iterators are the idiomatic approach. And in fact, even a for loop is syntactic sugar for an iterator. Iterator is a trait, which means there are many possible structs that can implement iterator. For example, vec and slice have a number of functions that can return iterators. This includes, but is not limited to, iter, windows, extract if, and more. Iter is fairly common on collections that can be iterated over at all. It returns an iterator over the items in the collection one by one, as you might expect. The output here prints each number in turn. Windows, on the other hand, is slightly more interesting. The items provided in each iteration are a rolling window, viewed as a slice of arbitrary length. This results in printing pairs of numbers, because we chose a window size of 2. Both of these functions return a struct that implements iterator that controls how this iteration happens. A more interesting iterator is provided by extract if, which also happens to be one of my personal favorites. This accepts a range to operate on and a closure to test the items. If the item passes the test, it is removed from the original vec. This leaves all the items that failed the test in the original vec, and all the items that passed the test become available in the iterator. This produces a log for each item before logging the entire original vec, which has now been mutated, removing the items. Iterators can also return a single value, such as using sum to sum all the items, all to check that all items pass the test, or a function like findMap, which will find an item that passes a test and then transform it into a different type. This can be very useful when dealing with operations that can fail, like parse. Here's an example of an iterator that finds the first parsable number in a vec of string slices. Notice how the parse for tree fails because it's not a number, and this returns the number 2, which succeeds. Once you have a struct that implements iterator, you can use any of the functions on the iterator trait to continue to operate on the items. This includes functions like map, which can transform one type of value into another, or functions like filter, which can filter items out. Note, however, that iterators in Rust are lazy and do nothing if they aren't called. We can call it manually with next or with a for loop, or use a consuming iterator function like collect. One nice piece of Rust is that if you construct an iterator and don't call it, the compiler will actually warn you. Here's an example program that will produce that warning and show the original vec was not modified. And here's the warning, which says an unused map that must be used. In this case, the map function returns a struct called map that implements iterator. You can also place this must-use attribute on your own types, but we'll cover that in the future. We can use collect to collect items into a new vec of the appropriate size. Rust iterators provide a base for more advanced operations as well. For example, Rayon provides data parallelism on iterators. Rayon guarantees data race-free executions and takes advantage of parallelism when sensible based on workload at runtime. To parallelize an iterator, it can be as easy as using pariter instead of iter. And building maintainable software includes a whole host of other functionality. In this case, Cargo includes a subcommand, for example, for running tests, and Rust provides support for authoring tests through the test attribute macro. If you initialize a new library crate with Cargo new, it will come with unit tests, but Rust also supports integration and documentation tests natively. The lib.rs in this new project includes a function called add that is tested in a module that only compiles if we're running tests. The whole module is gated based on whether test is set or not, which is something that Cargo will do for us when running Cargo test. Tests in Rust are regular functions. If they return a result error or panic, the test fails. And since tests are regular functions, we can identify our test functions with the test attribute macro. Running Cargo test now produces pass and fail output. Even more approaches to testing are supported by the crates.io ecosystem, including snapshot testing, table-based testing, property-based testing, mutation and fuzz testing, and more. Rust also comes with documentation tools built in. Running Cargo doc on the library we just initialized produces the documentation that was written for all items as a web page. By default, this doesn't include a whole lot of content, but you can turn on a lint to warn when documentation isn't written for an item, which is what I do in my projects. In our recent testing ground crate, open Cargo toml and add a Rust lint that warns when compiling if documentation isn't written for an item. Then when running things like cargo test, cargo doc, or similar commands, missing documentation will generate a warning. This shows warnings for missing documentation for the crate itself, as well as the add function. We can add documentation using two different comment syntaxes. One is the inner attribute, which documents the thing above it, and one is the outer attribute, which documents the item below it. The inner attribute is // exclamation point, and the outer attribute is 3 slashes. Content in these comments is written as markdown syntax, and here we've included an example in the documentation, which gets compiled and included in the tests that run, ensuring that our documentation is never out of date. Finally, Rust includes support for examples. In a new file in examples/adds.rs, write a new program that uses the testing ground library to power a binary program. This example can now be run with the example flag. This example is named after the file name by default, so we will run cargo run example adds. The examples directory is a very common feature in Rust projects because it can show real-world usage of library. So if you ever find a crate on crates.io that you want to use, you can go check out the GitHub repository, which may have an examples folder showing how to use it. And that's it for an overview of the Rust language today. There's a lot that's been left out in the interest of keeping this hopefully under half an hour. We'll find out when I edit this. You can look forward to the deeper introduction to the Rust language content over on rustadventure.dev if you decide to move forward with Rust from here. Or you can come hang out on stream when we develop the content, or come ask questions in Discord. Links are in the description. That's it for me for today. I hope you have a great rest of yours, and I'll see you in the next one.